Hi. Okay, so last time we talked about some of the propositional logic operators, and or not, and some of the more the sort of second step ones, exclusive or, implies, if and only if, that kind of thing. So we did some topics last time, but last time was kind of a long video, so I moved some of the topics to this second video, which is a little shorter, and where we're going to talk about predicate logic. Okay, so let's start it. So let's see here. The second topic, the first topic for today, is I want to talk about and or, as you sometimes run across them on computers. So you'll remember that the and operator comes out to be true exactly if both the P and the Q are true. So P and Q comes out to be true only if P and Q, both of them, are true. So if the first one is false, right away you know there's no need to test the second one, the and is going to come out false. Turns out that can be convenient. That can be very convenient, and that was first noted by John McCarthy, the famous computer scientist who at the time was at Dartmouth but then moved on to MIT, went on to invent Lisp and a number of other very sort of foundational work that he did in the early days of computing. So he pointed out that when you make an and operator, and operator, you can make it a short circuit operator. That if the first thing comes out false, then there's no need to do the second thing. And furthermore, pointed out that that's a convenient thing sometimes. Here's an example. So I've written a command. It's supposed to be for a shell script. It's supposed to be for a bash script. So if the log file exists, and you'll remember that double ampersand is often the way to write down logical and. If log file exists and mail log file. So I'm going to check whether the log file exists, and if it does, I'm going to mail it. If the log file doesn't exist, the and operator will never go on to run the second command. If the log file does not exist, if this comes out false, then the second command will never get touched, so you'll never get a failure from trying to mail a file that doesn't exist. That's called a short-circuited operator, and you see that a lot, and in particular you see that a lot for AND, for AND. Okay, it's a little bit peculiar mathematically because it means that if you go back and look at the definition of AND, P AND Q is exactly logically equivalent to Q AND P. But that's not true here. Here, if you had written them in the opposite order, mail log file and log file exists, you would have had a failure in the script. So it's a little bit mathematically, it's a little bit peculiar. So I made it a topic because it's not really mathematical, but it's of interest. It's something that a person sees. Okay, the next thing, I discussed when we introduced the if-then statement, the implication operator, the arrows operator. I discussed that it needs a little bit more conversation, and here's the conversation. So I want to contrast these two statements. The statement, if Babe Ruth was president, then life exists on other planets. And the statement, if Mallory reached the summit of Everest, then 1 plus 1 equals 2. So Babe Ruth was president, of course, is false. Babe Ruth was never president. Mallory reached the summit of Everest. We don't know if that's true, but 1 plus 1 is definitely 2. So what we're looking at here is we're looking at an implication statement with a false antecedent. And I don't know, does life exist on other planets? So a false antecedent, and here the antecedent, I don't know, but the consequent is true. Both of those, if you look at the definition of implication, both of those evaluate to true. F arrows T evaluates to true, so does T arrows F evaluates to true, and T arrows T evaluates to true. So as long as the antecedent is T, the statement as a whole evaluates to true. Here, it's in some sense the mirror of that. As long as the consequent is T, the entire implication evaluates to true. So both of these sentences would evaluate to true in our definition of implication. And a person can think that this is strange and maybe not exactly how everyday language works, although mathematics isn't exactly everyday language. But you can ask, if you're focused on mathematical language, why are you doing this particular thing? Very sensible. And the reason is that we will find ourselves very often making sentences like the following, and we want them to come out to be true. If x is a perfect square, then x is not prime. Again, if x is a perfect square, then x is not prime. And of course, we have in mind that if it's a perfect square, why it factors. 9 factors into 3 times 3, so that automatically makes 9 not prime. So we want this sentence to come out to be true, even in problematic cases like this. Okay, so we'll try some various x's and we'll see what happens. If you have, for example, an f arrows statement, if you take x to be 6, you get f arrows t. 6 perfect square? No. 6 not prime? Yes. So f arrows t. Well, we want f arrows t to come out to be t then, since we want this statement to be true for all cases. All right, so we'll try x to be 3 to get f arrows f. 3 perfect square? No. 3 not prime. 3 is prime. So 3 not prime, f. So f arrows f. So we want f arrows f to come out to be true. And likewise, by taking x to be 9, you get that you want t arrows t to come out to be true. So for mathematical conversations, it is a convenience to define implies in this way. Now, whether you want to define implies in the case, for example, Babe Ruth was president and life exists on other planets, where there's no material connection between the beginning of the sentence and the end of the sentence, and Mallory reached the summit of Everest, we'll never know. That's a question for philosophers. But in mathematics, we take the implication to be. In mathematics, we take the implication operator to be defined the way we defined it. If you want to call it as a convenience, then we'll call it as a convenience. Okay, last topic here, one-time pads. So the exclusive OR operator is invertible in the sense that if you know the output and one of the inputs, then we can find the value of the other input. Maybe I should go back and help a person work through that. Exclusive OR, exclusive OR, exclusive OR, exclusive OR. Here we go, exclusive OR. So if I tell you the output is T, and I tell you that Q is T, then you say to yourself, well, only 2 outputs have a T, so it must have been the F line. If I tell you the output is T and Q is F, then you can say to yourself, it must have been that P was T. Likewise for outputs of F. If I tell you the output is F and Q is F, it must have been that P is F. If I tell you the output is F and Q is T, it must have been that P is T. So in that sense, knowing the outputs and one of the inputs, you can go back and reconstruct the other input. So in that sense, exclusive OR is invertible. A small observation, but it turns out to be an important observation. And here's why it's important. You start with a string of random bits. I grabbed this from the random bit generator on my computer. Most modern operating systems come with a source of randomness, and I grabbed this from mine. So it might look to you like it's not random. There's got an awful lot of zeros in it, but I'm telling you, it came from the random generator on my computer, and so that's what I did with it. Okay, I put that in as the second line. Can you see it here as the second line? Now, I want to send somebody a message, HELP. So I encoded H, E, L, and P in some binary code. This particular one happens to be the Baudot code, but you could have used ASCII. I just used what I used. Now for the encoding of that message, I take 0 exclusive ORed with 0. So that's F exclusive OR F, and I got 0. 0 exclusive ORed with 1 gives you a 1. 1 exclusive ORed with 0 gives you a 1, 0, 0 again, and there's the 1, 1. 1 exclusive ORed with 1 gives you a 0. If you look up 0, 1, 1, 0 in the Baudot code, it's an I, capital I. And so now I go into the telegraph operator and I ask the telegraph operator to send I, null, L, Y, this kind of stuff. It gets to the person at the other end. The person at the other end is able to go in reverse, just as we just described. The person at the other end can say to themselves, okay, I is 0, 1, 1, 0, 0. Going in reverse, if the output is 0 and the second thing was a 0, I know the input must have been a 0. If the output is a 1 and the second thing was a 1, I know the input must have been a 0. And like that, it's a little boring, but of course that's why we have computers. Computer can do this very, very rapidly, go in reverse, and the person who received the message will be able to read off HELB. This is, in fact, the world's only provably unbreakable encryption system. That if you start off with a collection of random bits, you can generate these, for example, by sitting in your office flipping coins, if it comes down to that. If you have an office, I guess, sitting in your room and flipping coins, if it comes down to that. So if you have a sequence of random bits and you share that sequence with your friend, it's traditional to write them on a piece of paper, and each party gets one copy of the piece of paper. It's called a one-time pad, because after you've sent a message using this sequence of random bits, you have to rip it off of the pad and burn it. And now you have another sequence on the pad underneath, on the piece of paper underneath on the pad. This is the world's only provably unbreakable encryption algorithm. Okay, so this small observation about exclusive OR turns out to be extremely important. Okay, so those are the topics from propositional logic. Now we're going to turn to predicate logic, which actually is we're only going to look at a very small piece of predicate logic. All right, so you'll remember the idea here is that when we did propositional logic, we said we're going to focus on statements that have a definitive true or false value. So I might say that Montpelier is the capital of Vermont. That has a definitive value of true. Burlington is the capital of Vermont. That has a definitive value. It happens to have a value of F, but anyway, it's the definitive value. Now, there are two kinds of ways you can fail to have a definitive value. One is by not having any value at all, and the other is by having a variable value. So if the statement involves, for example, x's, then it's a problem. Okay, so if I consider the statement for any even number x, the square is a multiple of 4, that's a perfectly ordinary mathematical statement. We have to be able to make sense of that statement. What makes it make sense here is the presence of the for any. So there's an x. If I didn't have the words for any, if I just said, given x, the square is a multiple of 4, that would be an indeterminate sentence, because it is true for some x's, it's not true for other x's. But when I add on for any even number x, okay, then I'm in business. Okay, so I need the vocabulary to be able to write that down. How do I say, for example, that a number is even? And the answer is I'm going to consider that a Boolean function. I'm going to do what you would do in programming. This is a function whose output is t or f. It's traditional to write it in this way, is underscore even. You can write it however you like, but I'm in the habit of doing that. So is underscore even is the name of the Boolean function, and its input is x. X is supposed to be an integer in this case. And of course, is even x comes out to be t, only in the case where it's an even integer. So is even, if you feed that a 3, it'll come out to be f. If you feed it a 5, it'll come out to be f. If you feed it a 10, it'll come out to be t. The mathematical jargon, usually don't say Boolean function mathematically, you say predicate. So a predicate, and it's just a Boolean function. It's what you know, what you're familiar with. It takes in one or more inputs, and it gives an output of either t or f. So a predicate is a Boolean function. An example of a predicate is the less than statement. So less than xy comes out to be true if x is less than y. You can also have more than 2 inputs, 1 input, 2 inputs. You could have 3 inputs. Pythagorean xyz comes out to be true exactly if x squared plus y squared equals z squared. You could have 10 inputs or 100 inputs, or we won't ever do that, but you could have as many inputs as you like. This for all that we had at the beginning, that tells you how many of the x's you're talking about. We're talking about all of the x's. So that's called the quantifier. It tells you how many. So the statement is even x is neither true nor false, but the statement for all x is even x does have a value. Well, it says it's true, but it should say false. I'm sorry about that. That word should be false. It's a typo. That's called universal quantification, because I'm saying for all x's. you denote universal quantification by it's the letter A upside down. They literally in the old days they took an A out of the and they turned it 180 degrees and they stuck it back in again. So it's literally is an upside down A. For all x that are integers, and then the square brackets denotes the what the for all is pointing to it is even x. Okay, and that would have a value of false. I'm sorry about the typo. The other quantifier that we will usually run across is there exists an x such that is even x. That's called existential quantification for the obvious reason, and it's not going to be a shock to you that to denote there exists, you take an E and you turn it upside down and you shove it back in there. Now in this computer age you don't have to do that, but in the old days they physically did that. Anyway, there it says there exists an x in the integers where x is even. And that statement is true. I said also true, but again I must have been half asleep when I typed that. All right, so let's go down to the statement here, a more sort of sensible mathematical statement. For all x, this says if, see the if then? If x is divisible by 4, then x is divisible by 2. So this particular statement, of course, is not especially interesting to us. What's interesting to us is that the kinds of conversations that we can have, the kinds of conversation you would have, for example, in a 7th grade algebra class, are perfectly write downable. We have a formal system to write them down unambiguously and make perfect sense of these kinds of statements. Now, all children want to learn. I can't write that down in any formal way. But mathematical statements we can make perfectly good sense of. So here, the integers we're talking about is called the domain of discourse. It doesn't really make sense to talk about divisible by x4 if x is a real number, so I'm talking about the integers. That's the domain, or sometimes called the universe of discourse. Often the domain of discourse is clear from the conversation, and so you won't be talking about it. I mean, if you're in calculus class, then the domain of discourse is probably the real line. So you don't spend a lot of time talking about that. But you can put it in, and that's where you can put it. Okay. Here's another example. Don't like to have one example of new ideas. So 2 examples. I want to say between any real and the number that is 1 higher, so between x and x plus 1, there is a real number. So if, for example, x is 3.14, then I'm asserting that there is a y between 3.14 and 4.14. It's not the world's hardest sentence, but I wanted to write it down in some sensible way. So how do you write it down? It says, for all x in the reals, you see the domain of discourse there exists a y in the reals where x is less than y, and, remember the and symbol? Y is less than x plus 1. You'll notice the point of the domain of discourse there is that if I change those real number symbols to the integers, and you try to assert, for example, that there is an integer strictly between 4 and 5, the statement would be false. So the domain of discourse does matter in some cases. This is an example of that case. Okay. The main point I want to make about quantifiers, I guess I have 2 main points, but first main point I want to make about quantifiers is that this business where you saw on the previous example where we alternated quantifiers, it has a there for all and then it has a there exists. Or if you go in the other order, if you go there exists and for all, that's when statements get complicated. So a person can, in some sense, make sense of what is complication by trying to understand, when you write the sentence down formally, how many times do you switch back and forth between the quantifiers. So for all x, there exists a y, where y is greater than x, is a very different statement than there exists a y, where for all x, y is greater than x. Let's think about those 2. For all x, there's a y where y is greater than x. Yeah, that's true. That would be the case, for example, if y is x plus 1. What about the other? There exists a y where for all x, y is greater than x. That's not right. Because if you take, for example, y is 100 million, Is it true that for all x, y is greater than x? Is 100 million greater than all? No, it's not. 100 million is not greater than 100 million and one. So this is true, this is false. So this alternation of quantifiers is sort of the moment when a person has to start scratching their head. Here's a cartoon that says the same thing in a somewhat more amusing way. I hope you can read it. So this is Dilbert and his girlfriend. I think that's his girlfriend. I don't actually read the cartoon very often. I believe she says there is one true soulmate for every person. He says he must be very busy. She says, I meant one per person. She says, your way would be stupid. And he says, can your soulmate be a monkey? So the difficulty is that in her sentence, she's got the quantifiers wrong. There's a big difference between there exists an x in the set of persons, where for all y in the set of persons is soulmate of y equals x, and the assertion for all y there exists an x. For every person there is a soulmate is very different from there is a person who is the soulmate of everyone. So the alternation of quantifiers is kind of the moment when you have to put your pencil down and say to yourself, is that right? Kind of thing. Here's an example that dramatizes that. We won't typically work with things this complicated, but if you've taken Calculus 1, then you've run across a definition of limit. The limit as x approaches c of f of x is equal to L when, by definition, it's complicated. My point is that it's complicated. That's why it's here. For all epsilon, there exists a delta where for all x, and before we go on here to what's inside the square brackets, for all epsilon, there exists a delta such that for all x alternates quantifiers a couple of times. So it's kind of a head scratcher of a head scratcher. So for all epsilon, there exists a delta such that for all x, and it says if the distance from x to c is less than delta, remember c, it's over here. The distance from x to c is less than delta, then the distance from f of x to L is less than epsilon. And again, this is not calculus class. I'm not really so interested in the exact content of the sentence as that you recognize this as a complicated sentence, a sentence that it takes a person, a smart person in calculus class, a good long time to try to get straight. The number of alternations of quantifier is some rough measure of the complexity of a statement. So one thing quantifiers do for us is they help us to understand whether the statements are easy or hard. And then the second point I want to make about quantifiers is that the universal and existential quantifiers, the for all and there exist quantifiers, are related. If I say for all x, p of x, and then negate it, if I say for all x, p of x, and then negate it, that's the same thing as saying there exists an x where not p of x. Time for an example. If I say all dogs have 4 legs and then negate it, that's the same thing as saying there is a dog that does not have 4 legs. Let's try the next line. If I say there exists an x, p of x, and then negate it, that's the same thing as saying for all x, not p of x. So let's take an example. If I say, there exists a car with 5 wheels, and then say, no, that's not true. It's not true that there exists a car with 5 wheels. That's the same thing as saying for all cars, it's not the case that they have 5 wheels. So again, the negation of there exists is for all, not. The negation of for all is there exists not. So there's some sort of relationship between these two. There's some sort of algebra. If you see the not for all, you can replace it with a there exists not. If you see not there exists, you can replace it with for all not. That's a kind of an algebra of the quantifiers. So here's a very typical example of using that algebra. If you see for all y, there exists an x, and then inside the square brackets is some statement, and we want to negate it, then I put a not in front of the for all. If you put a not in front of the for all, that's the same thing as saying there exists not. The rest of this is perfectly the same. So I took the not for all and exchanged it for a there exists not. Okay, well now it says not there exists. So I can change, as it says up here, I can change not there exists for all not. Not there exists for all not. That's what it says up here. Okay, not there exists for all not. And now I can go in and if I want to, I'm pretty much done here with the quantifiers, but if I want to, I can go even further. I can take this not, what's the negation of an implication? When does if then come out false? Do you remember? If then comes out false only when the antecedent is false and the consequent is true. When the part before the arrow is false and the part after the arrow is true. That's the only time that an arrow comes out false. Okay, so I now have the part before the arrow is false and the part after the arrow is true. And so in this way, you can do an algebra here. In this way, you can do an algebra of these statements. In this particular slide, the part that I'm most interested in is the part in the couple first lines. Not for all becomes there exists not. Not there exists becomes for all not. And you can go on to here. You can, for example, distribute the not p of x over the q of x and r of y. So I went on and did that. But the main point is the first couple lines. Okay, so I want to close with with an example of that exact thing, and then that'll end us for the day. So a much shorter video than last time. So p of x, p implies q is logically equivalent to not p implies not q. If I say, for example, that if you're a dog, then you have 4 legs, that's logically equivalent to saying if you're not a dog, then if you don't have 4 legs, then you're definitely not a dog. So if you have 4 legs, if you're a dog, then you have 4 legs, is equivalent to if you don't have 4 legs, then you're not a dog. Okay. So if I say for all x, r of x implies b of x, that's equivalent to for all x, if not b of x, then not r of x. Those two are equivalent statements. And there's a bit of a paradox in that statement. The paradox is if you go to apply that to the real world, somebody who's trying to prove that all ravens are black can prove it this way. They can go around the world finding ravens and checking off on their clipboard, yes, it's black. Or, logically equivalent to, they can go around the world finding not black things and checking that they're not ravens. So all ravens are black is logically equivalent to all non-black things are non-ravens. And that's a bit of a paradox because you can go around the world trying to gain evidence for all ravens are black by finding non-black things that are not ravens. That chair is brown, that car is green. So that's a very sort of counterintuitive way of going around finding green cars. It's kind of a counterintuitive way of proving that ravens are black. It's called Hempel's Ravens paradox, and it really is an example, it seems to me anyway, not a philosopher, but it seems to me an example that these applications are meant for mathematics, computer science, for a limited domain. It turns out I found a picture online of an albino raven just as a joke. Okay, very good. That ends the video, and we'll see you for the next time.